In this video, I will explain the definition of neural networks and the meaning of widths and depths of neural network. Okay. Neural network is a composition of simple functions. So here there is input x. Usually the input x has high dimensional structure, a vector or some image or whatever. And essentially the input value will be multiplied by a weight matrix and then added by some bias vector. So here I will use the notation a bracket number to denote the values or vectors at layer 1, this is A1, at layer 2, this is a bracket 2, and so on. So the nth layer activation values, neuron values, will be denoted by AL up to a capital L. Here the capital L denotes the number of layers. So here a capital L is the output of your neural network. And usually we do not count the input layer, the layer 0. So here we say this neural network is layer L neural network. Depth is L, this neural network. And we also have some loss function for every input x. We usually measure the distance between the true label y or true value y and the output of neural network. This is a bracket capital L. With this notation, x, the input x is equal to a bracket 0, and at each time we compute the GL from the weight matrix at layer L times the activation value from the previous layer plus the bias vector at layer L. And the AL, the activation vector, will have this definition, the activation function at ZL vector. Because from the definition of neural network, each neuron have this two-step computation. So each neuron compute this linear function and pass through some element-wise nonlinear activation function to get the AL vector. So this is the notations and definition of neural networks. Maybe you already know this from the video Stanford 231N lecture. Okay. So here the depth is capital L. Width, usually the dimension of each activation vectors. And sometimes, or some papers or some people say the width of the neural network is the maximum value among all dimensions of neurons. Okay, right. Then what is the meaning of depth and width? Why we have to have sufficiently large width and depth to have nice properties or to have very nice accuracy. Okay, so I will give you a very simple toy example. Let's say the input X is two-dimensional and we collect the data point with blue and red. Blue is class 1 data point and red is class 2 data point. And this two-dimensional space is the input space and the color represents the output label. Essentially, what we want to do for this data set is classification. We want to draw some decision boundary like this so that we can classify any new input data point very accurately, right? So this is the main goal of all kinds of machine learning. Neural network, when you just look at the last layer of your neural network, so this is the A bracket capital L, A bracket capital L minus 1, there is weight matrix WL, and there is bias vector. Essentially, this unit is almost just a linear classifier. From the A bracket L minus 1 activation vector, we just classify these feature vectors using some linear classifiers, which means we can draw just a linear line, this or this, to discriminate the blue area and red area. This is not possible using current form. Okay, so that's why we have a multi-layered neural network. Each layer can shift each point. Okay, so we can move each blue data point, each red data point, layer by layer, so that in the end we can easily classify red point and blue point. But when you keep the 2D space, when all the dimension of activation vectors are 2, so the width of your neural network is 2, then no matter which kind of linear transform you apply for each layer, so no matter which W matrix and bias vector you utilize, you cannot bring all the blue point to the outside of your red point. This is not possible using the linear transform, using weight matrix and bias vector. And the activation function also does not useful to bring all the blue point to the red, outside of red circle. Okay, so when you keep the 2D space, basically it is not possible to have very nice classification accuracy. But imagine you can increase the dimension. So you can increase the width of neural network from 2 to 3. Then you have one more dimension, like this. And there is some plane, subspace, and blue and LED on the subspace. Okay? When you make your neural network from A0 to A1, you increase the dimension, so you increase the width. Then essentially you have one more degree of freedom to control your data point. To do linear transform, you have one more degree of freedom. In that case, using nonlinear activation function and weight matrix and bias vector, you can actually perform very nice transformation, like bring the all blue point to the downside, bring the all your red point to the upside. This is possible. Okay, and using many layers, essentially in the end, you might have this kind of blue and red point. So essentially there are two plane, and all blue points are located the downside plane, all red point in the upside plane. And then when you project this data point from this viewpoint, then in the end you have all blue point here, all red point here. So which means when you assign this is x1, x2, x3 axis, and when you look at all the data point from the x2 vector direction, then in the end this is x1 axis, this is x3 axis, and all your blue point will be located the negative side of x3, and all the red point will be located on the positive side of x3 axis. With this blue and red, with the final layer, you can simply discriminate the blue and red point using linear classifier. There are many linear classifiers that can easily discriminate blue and red point. So that's why we have to have a sufficiently large width and depth so that we can very easily classify any kind of data point. Right?